What up? Welcome back, chat. Before we get started, can I get a quick, oh yeah? He knows. He knows. Cool. What's good? Bet. Sweet. All right. We're going to jump in. I can't do it. I'm going to break character. All right. We didn't have homework. Terribly sorry. Cool. We need a bell ringer of some sort. Ooh, I have a good one. I don't yet, but I will. Why? I don't know that I can help you a lot with that. Fair. If you want to hand it, like if it has to be like put together, concatenated, which is a fancy word for put two things together, it's called concatenating. It's a computer science word. I'm good with that. We already did all those. Should we do just a chatting one? Really? Okay. Gosh, you look good, Rafa. All right. The fact that the derivative of the natural log of u is u prime over u is huge. Were these supposed to be your homework? Did you do them? Okay. If you didn't, I'm going to give you 45 seconds because logs are so nice that 45 seconds is probably sufficient for both of these. Maybe. This one might be a little trickier. Okay. If you have it done and you feel really comfortable with it, I want you to check with your neighbors, see if they have it done, if they're comfortable with it, and if you can add any guidance, cool. If you can't, check with a different neighbor. Cool. But let's check out C together real quick. I might have already given it away, but if you didn't catch what I said, what rule do we need first? Quotient. So let's knock it out. Y prime is equal to, what's low? Okay, D high is going to look ugly for a second, but I promise it's nice. How do you find the derivative of natural log of u again? U prime over u. What is u of this? So what's u prime? 2x plus 2 over x squared plus 2x, u prime over u. So there's low d high minus, here's the high. And what's d low? It's 1. I'm not even going to write it. Times 1, right? Okay, all over low squared, x squared. Now at this point, do we have a derivative? Yeah, we could stop here. I don't know that I necessarily would, but you absolutely can. Is there any obvious, clean, and nice algebra that one could do? Are you looking at these ones? Or what do you mean the x's? My first thought is this, or I don't know whether, depends on what we're doing with it, right? If I had to solve it, I'd do a bunch of different stuff. The first immediate thing that I see is this is distributing in. So maybe we call it 2x squared plus 2x over x squared plus 2x. Maybe that's not worth it. And Rafa, I think now I assume I know what you mean, but we'll see. Okay, I don't know, and I'm not the authoritative figure. Is this nicer? Maybe. It's I don't know, kind of subjective. Rafa, can you be a little bit more clear? Because I think I know. It is. It is. Oh, for sure. Rafa, I like your suggestion. And again, it's so subjective. And don't bother erasing if you already have it. What could I factor out of this right here? If I factored an x out, I don't know why my 2 always looks different on that one. Weird. If I factored an x out down there, it would be x plus 2, right? And then there's an x out here still. When I view it like that, what convenient thing happens? Hey, they divide out. Cool. Like maybe that's a nicer way. I don't know. It's subjective. Everything beyond this is just going to be simplifying to some particular point. Whatever that point might be varies depending on the problem. Cool. The derivative itself, easy or hard? Pretty easy, I hope. If not, good news is we get a bunch more practice because these log things are super awesome. This one, immediately notice, this is just y. Is there a better way we could write this? Now, there's a ton of options here. The first thing that I would do is this. And I saw some people looking at this and going, oh yeah, now I'll do u prime over u. It works. What is the derivative of this? 1/2 x to the negative 1/2, and then that would get divided by x to the 1/2, right? Okay, that works. That's fine and dandy. Check your log properties for me real quick from yesterday. This does something. There's another change we could make if we wanted. If we have a power in my argument, what does it do? It moves to the front, right? Like I could view this instead, and notice no calculus has happened yet. I could either differentiate this function, or I could differentiate this function. They're going to give me the same answer, but they're going to look very different. One of them is going to be much more simplified than the other. Let's check both of them real quick. Like they're both pretty easy. I'm going to move this one here instead. I think the second way is legitimately way easier. And for those of you that might see it, you'll probably agree with it. But let's try this first. You said 1/2 x to the negative 1/2. That's u prime. So we're at y prime now. Over x to the 1/2. And what happens when you have x to the 1/2 over x to the 1/2? Something happens with the exponents. They subtract. So I think it's 1/2 x to the negative 1. Because negative 1/2 minus 1/2. And is there a better way you can write this? 1 over 2x. And we're done. There it is. Now, this gets gross because you have to be able and comfortable to use that exponent property, which maybe you are, maybe you aren't. If we did it this way instead, let's just see what shakes out. Boom. What do I do with the constant multiple? It moves in front of the derivative, right? It just stays. So here's 1/2. That's my constant multiple. And in this situation, what's the derivative of the natural log of x instead of u? 1 over x. Do we get the same thing? Exact same thing. Is one of them easier? Like this one I think is noticeably easier. This one isn't like mind-numbingly challenging, but definitely nicer if you take the second to rewrite it originally. Turns out it doesn't really matter. We get the same nice answer either way. Cool. All right. Are we ready to rumble? Baller. Okay. For this, we are going to see like the coolest thing ever right now, and it has a really scary name. I don't want you to fully do it, but I want you to start thinking about it. We have this whole new topic within the same section. So we're still in logs and stuff. I'm going to be completely honest with you. Log base a of x, I do not know the derivative. Like I just tried to think about it, and I glanced down at my paper and I saw it, and I thought, nope, I'm just going to try to remember it. U prime over ln, like I don't remember it. I just don't remember it. If I were to take a test, would I just hope it is okay and I don't run into that problem, or would I spend a couple minutes trying to study it? Hopefully not. Maybe. Do you guys, without looking, can you tell me this one? Or we'll say you. I don't remember it. Doesn't seem like any of you guys remember it. Let's make a deal. We're going to do the same thing on Monday. Wait, it's only Thursday. We're going to do that again tomorrow. I'm going to ask the exact same question. I'm going to try to memorize it tonight. I want you to try to memorize it tonight too. Cool. For the record, it is ULNA. I should have known that because it works the same as U times ln E, and it just falls out. Don't know why. I struggle to remember stuff too, though. Like, I'm not messing with you. Like, for real, I have no idea. Don't know why, it doesn't click. All right, anyway, we'll come back to that one. We get this awesome idea called logarithmic differentiation. Now, this is arguably the most powerful tool that you have yet to see with logarithms, and why we hit them so hard. There's a lot of study that's gone into logs. John Napier worked out with them because it turns out that if you have scales where stuff gets really far apart, like the solar system, for example, if you were to graph the distance from each planet is from the sun, it's not a straight line. Like, it just doesn't work. It's hard to model with because it does like wonky stuff. But if you use a log scale on the X and Y axis instead, you can linearize your data. So you can take data that's like really wonky and doing this sort of thing, and with the right log scale, you can make it a perfect straight line so that it becomes really, really easy for you to predict or use some particular model just by using the fact that logs exist. Now, in our stuff, we're just going to jump right in. I'm going to leave a note here. We'll fill these in. But here's the basic idea. Make hard problem easy. That's what this is for. We take really hard problems that would really honestly be awful to do, and we make them easy using logs. Now, easy is always a subjective word. I don't think that overall is this really particularly easy, but compared to the alternative, it is night and day. So here's what I want us to think about. We're going to do an example here, and we're going to just annotate through it. I want us to differentiate the following. Okay. Before we knock this out, I'm going to remind us of a couple rules. If I have, let's see here, the natural log of x to the n, how can I rewrite this? That's an n, not a u. N. This is n ln x. Okay. There's other properties. What if we took the natural log of xy? Ln x. So they're multiplying in here. What I use in my head is it's a product, right? Product plus. That's how I connect them in my head. Plus the natural log of y. There's one more common one that we see. The natural log of x over y, remind me. Natural log of x minus the natural log of y. Now, the most common mistake when we do this in pre-calc is these properties. Notice, we always pay attention to in the argument, right? People will try to have this, like ln of x plus y, and they'll try to use it, but we don't have a rule for that. It's only if they're multiplying in the product. Okay, these rules are going to become super important. Okay, on the side, when you guys take notes, do you fill up your whole page, or is there always awkward blank space? Okay, I want you to try this problem. I'm going to give you like 2 minutes to try it. You may not finish, and that's okay, but I want you to try it with the understanding that we're going to rework the exact same problem again here in a minute, because if 2 minutes isn't enough, we're going to see, can we make it enough? Okay, so for our first one, here we go. I want us to differentiate the following. We have y equals x squared times the square root of 5x plus 1 divided by 3x minus 2 to the third power. Okay, I'm going to pause the video. I'm going to give you guys like 2 minutes. I don't think you're going to finish, but I want you guys to start at least differentiating. Okay, we'll see. 2 or 3 minutes. Chat it out. I'm okay if it gets loud and crazy in here as long as it's loud and crazy about the calculus. Okay. Just to look at this. It's gross. There's so many rules that we would have to use. Like almost every single rule shows up in this. If I wanted to start differentiating, what's the first rule that we would use? We would have a quotient rule. Like, and I know that it seems weird because you might try to think about everything else, but because we have to do low d high minus high, like we need to start here. Okay, if we wanted to, and I'm only going to write a couple lines just so you know, we can start. Low is 3x minus 2 cubed D high requires a product rule between x squared and a chain rule, including the x to the 1/2, and it's really gross already. But here we go. D high. Okay, so first, times the derivative of the second, which I'm imagining right now. I'm not going to rewrite it, but this is to the 1/2 is what I'm thinking. 1/2 5x plus 1 to the negative 1/2, but there's a chain rule here, so it's really times 5 afterward. First times the derivative of the second, plus the second, gross, times the derivative of the first, which what's the derivative of the first? 2x. So that was low d high, so that's just that part, minus high d low, which is another chain rule, unfortunately, and it's 3 times 3x minus 2 to the 2 times 3x. It is just 3, thank you. Now, this problem is already awful. Like, I have a gigantic screen and I'm running out of space. Did you guys also run out of space on your page? Like left to right? Okay. The good news is all over low squared, which is actually not that bad because it's just 3x minus 2 cubed squared is to the 6th. Okay. If you're pretty good at derivatives, do we have a derivative here? All right. Now, here's the bigger question. How long do we have to spend simplifying this to make it meaningful? It's going to take a while, right? Okay. Now, this derivative is not the worst thing that you'll ever see. Maybe it's the worst thing that you've seen so far with regard to calculus stuff, but it's just being able to employ all these different rules, right? Can we agree that this is kind of awful? The good news is just maybe, there is a better way. Let's see if we can agree that there's a better way. Okay, I'm not gonna like erase it. I might just on mine. Anybody not able to follow the stuff? Like, I didn't really talk it out, but could you see where I was getting my stuff from? Anybody not quite sure why I did something just here in this first little part as I was trying to differentiate it like normal? Anybody not saying that because you're shy to admit that you're the person that doesn't see what was happening as we were going? Eyebrows are really what I look for. Cool. All right, so don't be embarrassed. It happens. This is awful. Now, each individual rule I've seen you guys do, and I'm pretty comfortable with it, but when you start shoving them all together, it does get worse. Here's my suggestion. Yuck. Could we rewrite it first? Have we ever done that? I think so. Now, the only thing that I'd rewrite, and this is up to you if you want to include the single step, square roots aren't very convenient when it comes to actually taking derivatives, right? Like, they're gross. What do we write instead of a square root? We write to the 1/2. So I'm going to rewrite this first like this. Now, it doesn't really change anything about it. It's the exact same problem, but I want to be very specific with this. Have we done any calculus here? No, not yet. We've just rewritten the expression with the nice powers. Now, just by doing that doesn't change a whole lot. It makes it maybe a little bit more clear why 1/2 and all this stuff showed up here, but it doesn't do a whole lot. Algebra says that if I do something to one side, it's okay so long as what? As long as I do it to the other side. The only thing I'm not allowed to do to both sides for right now, for our purposes, is to divide by 0. Right? I can't do that. That's like the one thing that's not allowed. It's taboo. Puppies die when we do that. Okay, so I won't do that. What could I do? And if you look at the name of the example, maybe there's kind of a guidance here. So the name of the example, I guess, is differentiate. But what's the section that we're in? Logarithmic differentiation. What do you think I might do to both sides? Let's take the natural log of both sides. And right now, it's not going to be super clear. This currently is an explicitly defined function. I'm just going to say take the natural log of both sides. And we're allowed to do this. Now, again, I just want to stress, no calculus has happened. Okay, we're going to have a lot of writing. I should have said this before. If you're at the bottom of a page, I'm going to have enough notes and annotations and stuff that if you're going to add them all, I'd probably just flip the page over. Okay, so check it out. Here we are. We wind up with the natural log of y is equal to the natural log of all this stuff. And I promise when we actually start using these and doing this, there will be so much less writing, but I want to make sure that there's enough, at least for this first one, that it's very clear what has happened. I've done just the same thing to both sides. That's it. Okay, in general, is the rule for the natural logs derivative easy or hard compared to some of the others? I think it's easy, right? U prime over u, I hope you think that's easier than doing all the other stuff. It's definitely easier than doing quotient with product with chains all nested together. Okay, here we're still not doing calculus yet, but we're going to use these to our advantage. These guys, I'm just going to copy them so that we can all see them. These are going to become our best friends for right now. So here we go. Y, yes, ma'am. Thank you very much. I would not have noticed. Okay, anybody else notice that I wrote a square instead of a cube? Did you write a square instead of a cube? Cool. Power in numbers. All right, that's just a typo. Sorry about that. It was cubed. Thank you, Bea. All right, so here we go. Right now, is this function implicitly defined or explicitly defined now? Did we solve it for y yet? Like we just unsolved it for y, kind of, right? This doesn't really look like it, but it is implicitly defined right now. Okay, so here's what we're going to do. This left side is awesome. I'm cool with it. I dig it. This side, I should have changed color for, you know what? I'll stick with red. Okay, we are going to expand using log properties. Now, last year in pre-calc, if you had me for pre-calc especially, there was a whole section, and I can pull up the test right now and show you, or pull out the textbook, where all that we did was two different directions. Either condense this expression using logs, or to expand it. We're going to expand this. Cool. So the left side doesn't need any work. Natural log of y. I'm good with it. Okay. When we look at this, we're going to do a bunch of expanding. The fact that I see a division says I'm going to do what between the logarithms? So let's look at it. And we're going to go step by step here. You may be able to do it all in one line of work. And if that's you, I'm cool with it. But for now, we're not going to. So I'm going to have a subtraction right off the bat. What is the first thing that I'm going to write? The natural log of what? Can we all, instead of making you guys say this big ugly expression, is it the numerator? Okay, so here it is. The natural log of the numerator minus the natural log of the denominator. Okay, and again, I want to stress, we are doing so much more work right now than I would expect you to do on every problem, but it's a good review in case you don't recall this expansion stuff. Okay, do we stop here? I don't think so. Okay, Rad, what's happening between this x squared and this 5x plus 1 to the 1/2? Good. Do we have a way to change multiplication using log properties? If we multiply in the argument, then we can sum the logs. So let's go one more step. And I'm not going to redefine this. If you want to say the sum rule or the product, you can. But let's do it. This thing splits into two pieces then. It becomes the natural log of what's my first piece? X squared plus the natural log of what's my second piece? Somebody else. 5x plus 1 to the 1/2. Okay, we are taking little steps. Again, I'm going to sound like a broken record. I'm just going to keep saying it. Small steps here, you can take much bigger steps. But this is hopefully good review, unless you guys all remember perfectly how to expand logs. Do you remember all this perfectly? Cool. So a little bit, I hope. Like, it probably looks familiar-ish. Okay, minus, and is there anything that we can do with this one? And I'll wait for now. There is something that we can do, but we'll deal with it because we're going to do the same thing on all the next ones. Okay. Natural logs are kind of ugly typically, but they are the good sign in calc. Is each of these derivatives easier than the one that we had a moment ago? Like, because the derivative of ln u is what? U prime over u. Now, we're not quite there yet. Is there any other property that we can employ? We have used the fact that division turns to subtraction. We have used the fact that products turn to plus. Any other properties that we might employ? Holy exponents. The natural log of y, where does this 2 move? So it becomes 2 natural log of x plus, what moves out front of this second piece? 1/2 times the natural log of 5x plus 1. Nope, we haven't done any calculus. No calculus has happened. We're just rewriting with logs. And it's very clear that that hasn't happened, because if any derivative has been done, what would have showed up over here? Y prime would have had to show up somewhere. We are only doing algebra so far. Like, no calc has happened yet. This last one, though, what could I write instead? 3 times the natural log of 3x minus 2. Now, in doing this, I think, and I don't know, purely subjective, maybe I don't think, is this very final thing that we wrote right here, is that nicer than this, in your opinion? Like, it looks simpler, except for its logs, which people typically don't like because you don't see them soon or early on in your education. They're kind of a novel or new idea. All right, at this point, we have fully expanded using only algebra. And we have a much, much easier derivative to take here. Okay, now finally, we're going to take a derivative. But again, just like we saw a moment ago with the log stuff, algebra dictates that whatever I do to one side, I also must do to the other. Okay, I'm going to try to cheat in one line, unless you guys want to rewrite the whole line. I need to take the derivative of what? So now, calc. And I'm going to be more specific. We'll say d dx. And everything gets a derivative. And I'm going to use my cheater notation here, just so you guys can see, so you don't have to write the whole line again. I would do this. This shows me that everything is getting its derivative taken with respect to x. Okay, remind me one more time the derivative of ln u. Okay, so let's do it all together, and we're going to even see one more cool piece. Now, our expression in the end isn't going to be super nice, just so you're aware. But the amount of work that goes into this, it took a little while. Some of you can probably do this in one single line, and you can pick it out piece by piece. We'll get practice with it. If I wanted to take the derivative of this with respect to x, y is not solved for yet. This has to be implicit differentiation. What's the derivative of y? Y prime, so there's u prime in this case, over what was u? Y. So there's a left side, u prime over u. I just used the rule. Equals. Now, all of these, notice they just have a constant multiple. It just moves out in front of the derivative. So we'll deal with it. There's a 2 times, what's the derivative of natural log of x? 1 over x. If you would rather just call this 2 over x right here and right now, I'm good with it. Doesn't bother me. Okay, plus 1/2. What's the derivative of 5x plus 1? This is our u expression again. 5 over 5x plus 1, okay? And each one of these, independently, we no longer have to think about nesting our chains and quotients and stuff. There's a lot of work to this still, for sure. But the work that we have to do is so much easier if we just spend that couple of minutes, if needed, to rewrite it. Okay, minus, what comes out of this one? 3, and what is u prime over u? Okay, at this point, I might take a second, and I will clean it up just a little bit, and I'll get your guys' guidance. What are we trying to solve for in this problem again? We're trying to get y prime. Unfortunately, I don't have it quite solved for y prime. I have it solved as y prime over y. What would we do to make this be just y prime? I'm going to multiply both sides by y, but I'm going to do two things in once, if you hustle. Okay, check it out. I'm going to hold off, and actually, I'll just do it right here. I'm going to multiply both sides by y, and then let's clean up all this stuff, just a little tiny bit. We're not going to make a common denominator and do all of that, but we will just clean it up a little tiny bit. What's 2 times 1 over x? 2 over x plus 5 over, and I need your guys' input. Do I write 10x plus 2, or do I just write 2 times 5x plus 1? Okay, I'm fine with that. I don't know if that's what I'd really do, but that's okay. Minus 9 over 3x minus 2. Okay. Now, there's one wonky thing about this. We could common denominator, and it's not pleasant. Do you guys think you could find a common denominator? I bet it has a 3x minus 2, an x, and a 10x plus 2, and you would have to FOIL it all out, right? Like there's a ton of stuff that would go into this. Not really my focus right now. Unfortunately, if I wanted to find y prime, typically we don't want a y mixed in, but we do have a y mixed in. If only I knew what y was. Well, if only I knew what y... Hey, this is y. Okay, well, we'll rewrite this one last little line. And again, I just want to stress, we're doing this super slowly and in depth. I lost it. Can somebody tell me what y was? Okay, all I've done is substituted in y, right from the beginning. And now this awful expression would have to be multiplied by this. And we're done. Riley, we got here, just so you know, and we multiplied by y, and we just cleaned it up a little bit. And then we looked at this and said, gosh, dang it, I don't like that there's y written in there. But this is the very first thing that we wrote in this problem. We just plugged y back in. Now, at this point, you could spend the next 20 minutes, maybe not that long, I don't know, depends each person. We could clean this up and make it look a little bit nicer. But do we have the derivative right now? And I legitimately don't know. Is it easier to do this, in your opinion, or would it be easier just to do the chain with the product with the quotient? I think this, I wholeheartedly think that this is easier, but you could also disagree, and I think that you could also be right? It's super subjective. Okay, now, as we go through this, the hardest part of this problem is not the derivative, right? That's the easy part. The hardest thing to do is to be able to recall how we expand all these logs. I want us to do another one together real quick, just to practice with expanding the logs. Okay, and I guess I'll let you guys pick. Are we doing this one together, or do you want to try one on your own? Or with your neighbors? Okay, so let's see if we can't find a gross one to do here. I don't want a terribly gross one, but I want one that's kind of gross. That's one we just did. Okay, so let's check it out. On B, is this B? Yep, it's up to you. I would encourage you to use logarithmic differentiation because it's going to make it way easier, but it's your call. Unless I misheard your question because it doesn't look like I answered it. I'm going to write way less. Yeah, sorry, I wish I could give you more specific. All right, here we go. Either logarithmic or with every other rule combined together, psych, do it logarithmically, do that. X times x squared plus 3 to the 1/2. And we're going to divide this bad boy by 1 plus x. Now, I do want you guys to, before we do any calc, I want you to rewrite this using those log properties. We're doing this instead of doing a quotient rule with a product rule with a chain rule connected to it. This is the alternative. Take the log of both sides, and then I'm going to add a little bit more. Find, and you can write this after the fact, the slope of the tangent line at the point 1, 1. Okay, so first big thing, I'm going to give you guys a head start. I want you to expand the log. If you do it in one line and it's correct, I'm good with it. If you have to do it in multiple lines, I'm good with it. Cool. I'll give you guys a minute.